Welcome to lecture 31. In this lecture, we will have a discussion regarding two types of synchronous generator. One is known as a salient pole generator. Another is known as non-salient pole. Now, what does the word salient mean? In our daily life, we use the word salient like salient feature of this mobile or salient feature of this book, something like this. So the word salient means something which is projected. Now, how it is related to synchronous generator? Now, synchronous machines are mainly used as generators. So generators, there are major type of generation. One is a thermal power generation where we use steam turbine, and another is a hydel power station where you use a hydro generator. Now let's first look about steam turbine. In steam turbine, what is done? There is a turbine which somehow converts the heat energy into a rotational energy, and it rotates at a high speed. Now you require mechanical arrangement to bring down the speed. So how much you will bring it down? So the minimum number of poles that we can have in a machine is 2. So with 2 pole, what is the speed of the machine? Ns is equal to 120 into F by P. If you substitute P equal to 2 here, you will get 120 into, for a 50 Hz system, 50 by 2, that will be equal to 3000. So a steam turbine will rotate at 3000 rpm. It is almost universal that a 50 Hz steam turbine will rotate at 3000 rpm. Why we will not make it 1500? Because if you make it 4 pole and bring down the speed to 1500, then you will require more mechanical arrangement to bring down the speed from the high speed turbine to 1500. So it is already rotating. I'll say that the mechanical arrangement requirement will be more if we bring down the speed. So the steam turbine will always rotate at 3000 rpm. Now, how is this rotor construction dependent on the speed of the machine? The power rating of a generator, if we write the kVA rating or MVA rating, whatever you would like to say, is proportional to D square L. What is D? D is the diameter of the air gap and L is the length of the machine. Now, if you have a 3000 rpm machine, what you will like to have, there is one more thing that I missed here, is that uh, the if say this is my rotor, and these are the windings of the rotor, and outside this is my stator, and on this side are the stator coils. This is how throughout the periphery there are coils like this. On the rotor, the coils are placed like this, and on the stator, the coils are placed like this. Now, when the rotor rotates, say this rotor is rotating like this, so you can understand that from the law of physics, there will be a tendency for this coil to go out. Since it is just put in a groove like this, there will be a tendency for this coil to go outward. This is known as centrifugal force, and this force is given by m omega r. What is m? Mass of this one. What is omega? The angular velocity with which it is rotating. What is r? Radius. Now you cannot reduce the m, the mass of this coil. You cannot reduce omega, the speed is decided by this, but you can reduce r. So if you make the machine smaller and smaller in diameter, this force, the centrifugal force that is experienced by this coil will be small, and it will be easy for the machine to fabricate the machine. What is the difficulty? You have to make some arrangement so that the coil do not come out of the slot. So these arrangement will be lesser if you make the diameter of the rotor smaller. So for this, a steam turbine is always smaller in diameter. Now, if you make it small in diameter and want to attain a particular kVA or MVA rating, what you can put kVA or MVA here, it is the same. If you make this small, sorry, if you make the diameter small, you have to increase the length so that this you can attain this value. So a steam turbine will be smaller in diameter and longer in length. Now you can always argue like this, that I will make a generator which is as thin as a wire and as long, maybe a half a kilometer long. So this is not a practical thing, because if you have a generator, it is supported at two end with bearing like this. So if you make this long, very long, then in the middle the shaft will get bent like this. So we don't want the shaft to get bent in the middle. So based on that, some optimum length has to be chosen. But definitely for a steam generator, it will be longer in length and smaller in diameter. It will look like a cylinder. From my understanding, the diameter of a steam generator can be equal to half of the size of the classroom in which we take class, and can be long as two of this classroom. It is quite long but shorter in diameter. Now let's come to idle turbine. In idle turbine, the turbine rotates at a very low speed. How much low? For example, the Bhakranangal Dam is a idle power plant and it rotates at 166.67 rpm. Now, from where does this such a number comes? It means that the machine has 32 numbers of poles. You can substitute it here like this: ns equal to 120 into 50 by 36 numbers of poles. So if you substitute, if you calculate here, it will come to be 166.67 rpm, 166.67 rpm. So since there are 36 numbers of pole, to generate a 50 hertz voltage, you will rotate it at 166.67 rpm. So why we are rotating it at this one and this one at 3000 rpm? The reason is the turbine. This turbine operates at a lower speed. This turbine operates at a higher speed. So our machine has to match the turbine. These are the requirement from the turbine side. Now here we say that the rotor is a circular thing with number of coils on this, and what we need is only one north pole and one south pole. Two pole machine. Here we require 36 numbers of poles. So to make a machine with 36 number of poles, what we do, say this is my shaft, this is the iron cylinder type of thing, cylindrical iron body which rotates, and on the shaft we put some projections like this, and on the top of the projection we place the poles. Why we do like this? Because this area of this pole is not sufficient to accommodate 36 numbers of poles. You cannot make the pole very small because you need to produce a particular value of mmf. From how we will calculate the value of mmf? We know the rotation in the machine, the speed at which it is rotating. We know the induced voltage that we want to generate. What is E? E is equal to 4.445 phi ft. So this is the number of turns in the stator, this is the frequency, and this is the flux. So if these two are given, you require a particular value of flux to generate that voltage. You cannot have a very small value of flux. So the number of turns in the pole and the currents of the pole is finite. You cannot make it very small. Since you cannot make it very small, the physical size of the pole is also not very small. Say if you need 10 number of turns, and if you want to send 100 amperes through this, so the diameter of the conductor is fixed by 100 amperes and 10 number of turns. So the space it will take, you have to give this much space for the poles. So the pole has a particular volume or a surface area. So on this surface area, you cannot put 36 numbers of poles. So what you have to do? You have to increase this surface area. How to you can increase this surface area? By increasing the diameter. So how we have increased the diameter? By some projections like this. We don't make the whole body of solid iron because it will increase the cost as well as weight. What we do, we put some projections like this, and on top of this projection we put poles. So there will be number of poles like this. There will be number of poles like this on the periphery. All poles will have same dimension. Sorry, this one is smaller, but all poles will have same dimensions. Now what I want to convey here is that when you make an arrangement like this, say when you make an arrangement like this diagram is very poor, sorry for that. When you make an arrangement like this, here you see that this is my stator, this is my rotor, and this is the air gap. This air gap is uniform. Wherever you go, the air gap is uniform. Here if you look, this is my rotor arrangement and this is my stator, and on the stator and here we have stator coils. Now you see here the air gap is this much, here the air gap is more, here the air gap is this much, and here the air gap is again more. Here there will be one more pole like this, here I will have one more pole like this. Here the air gap is small, here again the air gap will be larger. So what I want to say here is that this is a salient pole machine, this is a salient pole machine, this is a non-salient pole machine. This is a salient pole machine. Why salient pole? Because the poles are projected. The poles are not on the rotor surface, but these are projected. That's why we call it as salient pole machine. In a salient pole machine, the air gap is not uniform. Here the air gap is smaller, here the air gap is larger. In a non-salient pole machine, this is a non-salient pole machine. In a non-salient pole machine, the air gap is constant. What is the implication for this? If the air gap is constant, my inductance will remain constant. That is, whether you calculate the inductance here or here or here, the inductance will remain constant. If my inductance remains constant, my access will remain constant. What is access? 2 pi f into L. If L remain constant, X will remain constant. So I can do an analysis assuming X to remain constant. So what I want to say is that till now whatever we have studied is for non-salient pole. That is, we have assumed axis to remain constant, and then we have analyzed the machine. So we have actually analyzed a non-salient pole machine. In next class, what we will study is a salient pole machine. What is the difference here? Here axis will not remain constant. Axis will have two parts. One xd, this one, This is called the direct access reactance or the smaller air gap, and another is XQ or this one corresponding to larger air gap. This represents the reactance here or inductance corresponding to smaller air gap, and this represents the inductance corresponding to larger air gap. So here I will do a calculation assuming that the reactance of the machine is variable and it varies with the location in the air gap. So in next class we will see how to analyze a machine if the air gap is variable. This type of machine is known as salient pole machine, and salient pole machine you will find in hydro turbines. Non-salient pole machine you will find in steam turbine. Thank you.